STAT340 Week 9. And again, this lecture is from 2022, where this topic was in week 12. So please notice that this year it's week 9. Apart from that, I think everything should be fine. Last week we talked about mixed models. We introduced the mixed models and we will just continue on that this week. So the first we will look at is what we call random effects models, which is only sort of a subtype, you could say, of mixed models. What is perhaps more important in a sense is that last week we focused very much on regression models in the sense that we looked at repeated measurements over time or over location. And we started out with the regression model, you could say, where we sort of expanded it by introducing random intercept or random slope. This week we will focus more on ANOVA models, analysis of variance. But it's not really different in the concept is of mixed models is exactly the same. But let's have a look at these random effects models a little bit special, because this is a sort of a phrase that you will come across. We will also use this opportunity to talk about a likelihood ratio test. And this comes as an effect from using another R package for fitting mixed models. We saw one last week. We will look at another one this week, which is perhaps even more used than the one we saw last week. There is a difference between this, how the output is from this, from using the NLME package that we used last week and the LME4 package that we will use this week. Or I'll actually use both of them, but the difference is in the output. There are no p-values for the fixed effects in the output from this LME4 package. And then we will see how we can actually compute some p-values using this likelihood ratio test. This is, I should mention, this is a very, very general approach to hypothesis testing and can be used well outside the sort of the framework of mixed models. So knowing a little bit about the likelihood ratio test is a good thing because it's so versatile in a sense. This can be used in all cases where you have a maximum likelihood estimate, actually. Yep. And then finally, we need to talk a little bit about crossed or nested data, because that's something we typically come across now when we talk about these mixed models. Mixed models quite often, or I should say, we often use mixed models for data where we also have nested data. And we will have a look at what is the difference between crossed and nested data. And also see how mixing the two or confusing the two can lead us to some pretty bad errors in our analysis. If you assume your data are crossed when they are actually nested, that can be a horrible mistake to make. And it's not so. It's a mistake you can easily do, I would say, at least in some cases. So we should be a little bit aware of this. Okay, mixed models. That's sort of the topic this week as well. And again, it's this chapter 19 in the R book. So, random effects models. What is this? Well, last week we talked about mixed models for the first time. And we saw that in a mixed model, we typically have some fixed effects, especially time then, if this is what we call longitudinal data, where we repeatedly measure the same person or object or unit over time, right? So time is at least a fixed effect, right? Or yeah, not random. We typically also have some treatments or whatever in addition to time, right? And these are also typically fixed effects because we are interested in how the different treatments impact the response, right? So fixed effects are there. In addition, we also have the random effects. And we saw that last week. We had these plants where we measured the root growth or the height of the plant itself. And we saw some other example where the experimental unit was a farm instead of a plant, right? And this could be a person or a location of some kind, right? The point is that you do repeated measurements on these units. And then we say that, and we are not particularly interested in the specific plants or the specific farms, so we describe them as just random samples out of a bigger population of many plants or farms or whatever, right? Individuals, you could say. So it's natural to describe them as random effects, random variables entering our models. A random effects model has only random effects. So that's really the difference to the mixed models in general, where you have both fixed and random effects. Here we have only random effects, which is not 100% entirely true, I would say, because we typically always have an intercept, which is sort of fixed. So I think it's fair to say that we also these are also mixed models in the sense, but they are without these treatments or time effects or anything like that. So they are a little bit special in some sense, but not. It's sort of mixed models. But the term random effect models are frequently used to sort of distinguish this from these up here. These are typically ANOVA models, or they are all ANOVA models, I would say. All the predictors are factors, which is what I call ANOVA models, right? The response is still a quantitative one, right? But all the predictors are factors with levels, like we saw in week 3 when we talked about ANOVA. But now all these factors have sort of random levels instead of fixed levels. All the levels are random. So in some sense they have infinite many levels. Even if in a data set we of course have only a few, but we imagine that these levels are just sampled at random from some normal distribution. So why do we consider the levels as random? Well, again, it's the same as we talked about last week. We are not so interested in the differences between the observed levels, but we rather see these levels as random samples from many possible levels. So it's more natural to describe it as a random variable rather than some fixed levels. And it's not really so difficult to come up with examples where this is actually the case. Let's see one example here from animal breeding, which is sort of a classical use of mixed models at NMBU. So we have this data set called sire unstacked. We will see it in a moment. Just let me explain a little bit what it is. There are data from 3 sires, and a sire is actually a bull, the same as you see here, right? Each of these sires has 3 daughters, and of course the daughter of a bull is a cow. And then we measure the milk production from each of these cows, each of these daughters. So we can say that for each bull or sire, we have sort of 3 measures of milk production. And this is of course interesting in terms of animal breeding, right? Because we are interested in if bulls are sort of, is it important to select the proper bulls here for breeding new cows that produce a lot of milk, right? You can imagine this is the setting. So for each sire, we have sort of 3 values of milk production, which is of course not entirely due to the sire, but at least that's what we are trying to find out now. Is there an effect of these sires on the milk production, right? Or how is the variation in milk production due to the sires? Okay. From week 3, where we talked about ANOVA models, we could easily sort of deal with this data set and ask, is there a significant difference in milk production between these 3 sires? And in order to answer that, we would fit a fixed effect ANOVA model, straightforward. We will actually do that in a moment. But notice in this question, between these 3 sires. So then what we are now focused on comparing these particular 3 sires. And we say nothing about all the other sires that are out there in the world. We only focus on these 3, and we want to compare these 3 to each other. Then we run a fixed effect ANOVA typically. We could also imagine another sort of question. Is there a big variation in resulting milk production between sires in general? So we are no longer interested in these particular 3 bulls. We are more asking, is it a point of selecting a particular sire here for breeding purposes? Or is this milk production more or less the same, regardless of which sire you choose, right? Because if it is, it doesn't matter which sire you choose, right? So I think this is sort of a more general question and something you would typically ask before you come up here, right? Because when you start comparing different sires, you must already have sort of investigated if there is any point in comparing them at all, right? And this results in a random effect model. In order to answer this question, we need what we call a random effect model. We will see now in a short. So what we actually are, we can sort of visualize the difference between these 2 questions, right? If this is our interest, we only focus at these 3 sires. So here we have the 3 sires, right? And we have the milk production on the y-axis. That's the response, right? What we are measuring. So from sire 1, we get this much milk from the 3 cows, the spread here. This one is approximately the same. This one is poorer, right? In milk production. So if we wanted to compare these 3, we sort of only focus on these 3 and forget about the rest of the world. But if this is the question, we are actually also interested in all the other sires that I have sort of grayed out here. We can imagine there are infinite many other sires out there. So we are actually more interested in, is there a variation here between sires in general big enough to make it worth go hunting for the best sire? Right? Because if this variation is small, it's little to be gained to go hunting for the best sire. There are other things we should go hunting for in order to improve milk production. Right? So that's the point here. Let's go and have a look in R and look at this data set and fit some models to see the differences. So here we are now in RStudio. I have created a new empty script for week 12 and stored it in my STAT340 folder. So now I'm ready to do some R here. And let's go to this lecture document and have a look at this section 2, the sire and stacked data. So this is a tiny data set to illustrate this random effects models. So let's just copy this code in order to load the data set. And we paste it in here and store. And let's run this. Sire unstacked. So here we can see the data set, and it's only 3 rows because this is actually a data set which is stored in a sort of a bad way, I would say. This is not tidy data. So here we have the sires, right? Sire 1, 2, and 3. And for each sire there are 3 daughters, 1, 2, and 3. And here is the milk production for daughter 1 of sire 1, milk production for daughter 2 of sire 1, and so on. So each sire has its daughters, right? So the first thing I would do now is to turn this into a tidy data set, and that's how things should be stored really in order to analyze data in R, or actually in any software, I would say. So how should we store the data? We should of course store this as 2 separate columns, 3 columns. No, it should be enough with 2 actually, because 1 column indicating which sire, right? That should be a factor, right? With 3 levels, sire 1, 2, and 3. And then another column with the milk production. We don't need to know which is daughter 1, 2, or 3, because this has no impact on our analysis now. Because even this is not the same cow in this case and in this case and in this case, right? Because the daughter number 1 means nothing here. So we actually need only two columns, I think. So I take the table. I use this pivot longer function. You should really learn how to use this one because it's very convenient. We put the names of the original table into a new column called sire, and we put the values into a new column called milk production. Then I make sure that sire is it's sire instead of just S. That's just for my own convenience, I would say. I didn't really have to do this. And then I mutate this factor so that it is really a factor. Let's run this code. We need to load the tidyverse packages in order to use this code. So let's do that first. And here we have, and now we have the sires table. Looks like this, right? So here we have sire as a factor with 3 levels, 1, 2, 3, 1, 2, 3, 1, 2, 3. And here's the milk production for each of the sires, right? The 3 daughters for each sire. And of course we want to plot. We should always plot our data. That's something you should never sort of skip. And I mean, since it's factors here, a box plot is often a good choice. Not always though. So try to experiment. But a box plot is often a good one. So you have the one factor at the x-axis, right, with the levels, and then you have the box plot, the response here as a y. So we can see there these are the behind each box is now 3 measurements, right? Okay. And imagine these are 3 sires out of possibly many. But the fixed model first that we mentioned, we could actually do as we did in week 3, fit a fixed model here where we say that the effect of sire called alpha I here is a fixed effect, so that I, 1, 2, or 3 is the effect of the different sires, right? And then depending on how we code the parameterization here, the default is to use the first sire then as a reference, right? And the 2 others as sort of variation of the away from the reference. That's the default setting in R. We will stick to that. So let's just fit this fixed model based on these data. And that's straightforward with LM, right? Milk production as response and sire as the, this is a simple one-way ANOVA. Couldn't be simpler. And here we have the summary, and we can see The F statistic indicates there is no real effect of sire here. The p-value is a little bit too large, I would say. So we can see that there are, this is the milk production of sire 1, and here is the change if you move from sire 1 to 2, goes down, yeah, we can see that. And here's the change if you go to sire 3, it increases a little bit, yeah. But nothing is very significant here, or at all significant, so actually the variation between sires is small, it looks like, yeah. But this was the fixed effect model, and this is something we typically would do if we want to compare these particular 3 sires, right? And we did this earlier by this pairwise comparisons. And let me just repeat what we did in week 3. So we used this mix LMR package and the function called simple.glht. So if I run this one, we will get this output here that you may remember from earlier, where we had this, we compare all the pairs, right? Sire 1 to sire 2, not significant different. Sire 1 to sire 3, not significant. And so none of them were actually significantly different. These 2 were the best candidates, right, to get some differences, 2 and 3. And we can see that they are also the closest to being significantly different. But and this is fine if you are actually interested in comparing these 3 sires. This is the way you should approach it. So the alternative approach now is, if we are not so particularly interested in these 3 sires, but rather want to estimate a random effect here of sire. So now, and notice I use this notation rule that I mentioned last week. I tried to stick to that. So when I had a fixed effect, I used the Greek letter here, alpha. Now I make it a random effect, and then I change it to a Latin A, in order to indicate to myself that now this is a random variable, right? And here you can see it's now normal distributed with the expected value 0 and with some unknown variance. And then we can fit this in exactly similar to what we did last week for the regression-like models, using the LME function from the NLME package. So we need to load this package first, and then you see we use the LME function here. The response is the same, and there's only an intercept here, no fixed effects, right? So this is a random effects model, and the random effect is on the intercept with sire as the grouping variable, right? So let's fit this model and look at the output. And here is the output, and you recognize this from last week. First we have this AIC and some other values up here. Then we have the random effects, and here we can now see the standard deviation. So the first one here is now the standard deviation of sire, right? This is the effect, this is the standard deviation between sires. And this is now the residual, the standard deviation between cows within each sire, you could say. So we can see that the variance in sires is, yeah, it's not super small, but it's smaller than this one, actually. And their only fixed effect is the intercept, which is perhaps not so interesting. Notice how this intercept is not the same as we got before, because the intercept we estimated in the fixed model was, of course, for one of the sires, but this is now for a sort of an average sire, right? And of course, this is significant because it's tested against if the intercept is 0, which is not really an interesting hypothesis, right? We know that milk production is not 0, right? So the p-value here is of no interest, I would say, because the null hypothesis is so silly that There's no, we can of course reject it, but that we could have done without any data at all, I think. So the whole point here are these estimates up here. That's the sort of what we are looking for now. How big is the variation between the sires, and compare it to the variation between the cows from each sire. So in this case, it looks like this variation between sires is rather small, right? Rather small, I would say, compared to this one. But it's not zero, and quite far from it too. Let's have a look at another way of fitting the same model, because it's important for you to know of this R package as well. So here we use the NLME package and the function LME from that one to fit mixed models like this. There is another R package which is also very popular, and perhaps even more popular, I think, for mixed model analysis, and that's this one, LME4. So you should install this R package as well. It's not part of the base installation. So here is how we can fit a model with this. And notice now the function is called LMER, Elmer. Right? So it's not the same function as up here. This is a different one. And the input is slightly different. The response we describe in the same way. And again, we have this formula saying that we want only the intercept here, no other fixed effects. But here is the difference. We now add also the random effect directly here to the same formula without having a comma and this random equals blah blah blah. So the formula contains both the fixed and the random effects, but the random effects are included in this way always. First, you have this parenthesis. You specify which sort of term in among the fixed terms are sort of influenced by your random variable, and then you have this vertical bar again, and then you specify the variable which should be random, right? So that is the same as up here, right? So since there is no other fixed effect here than the intercept, right? So that's the only thing we could put here now. But we could have had some other fixed effects here, and those could have been affected by this random variable. For instance, this random slope, right, model. Then you would have a fixed effect of time or something like that, and then this same variable would appear here instead of the 1. So this is a slightly more versatile way, I would say, of fitting mixed models. You can actually deal with more cases of data and models in this way than you can with this one up here. So that's why we should learn how to do it. And as I said, if you Google mixed models and R, you will typically more often come across people talking about this R package compared to this one. So let's have a look at this. We load the package, fit the model, and you look at the summary as before. And of course the output is also slightly different. Slightly different, right? There is no AIC listing here. The random effects are listed in a slightly different way. First, sire with variance and standard deviation. So I mean, this is just the square of this one, so you could have managed with only one of them, right? And then the residual here. So we recognize the same values of the standard deviations, of course, that we saw in the, because it shouldn't produce a different result, at least not very different. It could be some numerical changes, but that's all. And also the fixed effect. Notice there are no p-values here. There are no p-values. It's a t-value, but it's no p-value for the fixed effect. And that is something which is a little bit sort of strange or unfortunate, you could say, by this R package here. It doesn't give you a p-value for the fixed effects. There are some reasons for that, and you can actually look up the R package and type help p-values package, and then you will come to a help page that explains a little bit why there are no p-values here. Because actually computing p-values for mixed models is not as straightforward as it might sound like. But there are some suggestions on how you can do it, and we will actually pursue one of these now, which is using the likelihood ratio test. So let's draw some breath now and have a short look at this likelihood ratio test. Okay, to illustrate this likelihood ratio test, let's fit another model which is slightly different from the one we did up here. Up here we had one fixed effect, namely the intercept. And we saw that we got an output over here with a t-value, but not a p-value. Is this a significant intercept? We know it is, but because of the other output, right? But let's assume this was any fixed effect now, right? And we wanted to have a p-value here. How can we get that? Well, what we typically do then, we set up the null hypothesis, of course, right? And what is the null hypothesis? Namely, the intercept is 0 versus the intercept is not 0, right? And this could apply to any fixed effect, right? In this case, it's the mu from up here. You see the model equation up here. So this one is the critical one now. And then we fit another model where the null hypothesis is actually true. There is no intercept. And that's what I do here in this code. So let me just copy this code now and take it over here and paste it in. So notice now that in this model fitting here, I say again milk production is the response, but then I put -1 here instead of 1 that I did up here, right? So this model that I fitted up here and the one that I fit down here, you can see that this is the only difference. There is a -1 here instead of 1, and the rest is the same. And the effect of this is that we say fit this model here without an intercept. -1 means without this variable, right? Without the intercept. So we have the model with the intercept here, and we have the model without the intercept here. Let's do that like that. And now we can use what we call a likelihood ratio test. Because remember, when we fitted this model up here, we used a maximum likelihood or a restricted maximum likelihood approach to fit the model. So behind this model there is a likelihood value. And the exact same thing was here. Behind this fitted model is also a likelihood value. And the likelihood ratio test compares two likelihood values. And that's exactly what we do in this little code here. Let me copy in here. ANOVA, we have seen this ANOVA function before, but it changes behavior depending on what you input to it. So here we now have the first fitted model, and this should always be the simplest one of the two. The one with the fewest parameter, right? And this corresponds now to the null hypothesis, right? Where one of the parameters have been eliminated, namely the mu parameter, right? The null hypothesis is true, then there is no mu. This one disappears, right, from the equation. So we have only the two variances left here in this first model. That's the simplest one. This one is slightly more complex. because it has the same two variances, but in addition it also have mu, right? The intercept. And when you run this code now, you get this output here. Let me make the, yeah, this is big enough. So now you can see we compare the simpler model here to the more complex model here. And here is the log transform likelihood value for the first, and this is the log transform likelihood for the second. And here is actually the likelihood ratio statistic transformed into a chi-square value. So this is, or actually this likelihood ratio statistic, if the null hypothesis is true, this should follow a chi-square distribution with same number of degrees of freedom as you have a difference in number of parameters here, right? This one has 3 parameters, this one has 2, so so the difference is 1. So the chi-square distribution should have 1 degrees of freedom, and then you get a p-value. So this is how we can now sort of test this null hypothesis. Where was it? Here. This hypothesis testing here is now tested here, because if this is if null hypothesis is true, then this should be a chi-square value with 1 degree of freedom. But this p-value is so small that this is hardly the case. This is unlikely, right? A small p-value means we can reject the null hypothesis here. Mu should not be 0. There is a significant fixed effect here. And of course we knew that already, but this shows you the test procedure. We will actually see this again. Well, we just saw how we could use the likelihood ratio test. And let's dwell a little bit on this, because it's a little bit important to understand the idea behind this. It's a very general way of testing hypotheses. So I think it's worth spending a few minutes on this. Model selection using likelihood ratio test. So we have from earlier seen that model complexity is actually the number of predictors in our model. If you go back to week 2, 3, 4, something like that, when we talked about multiple linear regression, and also I think later when we talked about this principal component regression and stuff, the number of predictors in a model is the model complexity. This is not entirely true. It should actually be the number of parameters in the model. It's the model complexity, because in the case of the linear regression, the number of parameters is the same as the number of predictors. There is one regression coefficient for each predictor, right? Plus 1 variance then. Okay, so there number of predictors plus 1. That's the model complexity. But actually it's the number of variables. How can we find which predictors to include or exclude? That's model selection, right? And we have also seen this before. We did this best subset selection, or we did some backward elimination and so on. So variable elimination, best subset selection, and we need some criterion, and we have also seen one of them before, namely the smallest Akaikis information criterion. And this we also talked about last week, right? Smallest AIC. That's one way of selecting, what should I say, the best model out of several competing models. Another one is to use cross-validation, selecting based on prediction abilities. But AIC is a much used criterion. So, what I said earlier, model complexity is actually not the number of predictors, but number of parameters in the model. And for regression, there is one parameter per predictor plus one variance. So you don't make big mistake if you say that model complexity is the same as the number of predictors, right? It's the number of parameters, which is one more, always. In fixed ANOVA, there is one parameter per factor level, -1 because of this reference level, plus one variance again, right? So for fixed effect ANOVA, there is one parameter per level, -1. For mixed models, however, we must also remember that we now have several variances. So we have, of course, the fixed effects, whether they are regression coefficients or factor level parameters. But in addition, we also have several variances now, 2 or more. And they are also parameters. So they should be counted into the model complexity. So the more parameters you have, the more complex model you have, whether they are fixed effects or variances, these parameters, all the Greek letters. So we may simplify a model by eliminating fixed effects, of course, that's what we have done before, but we could also eliminate random effects in the same way. Actually, there is no way, also there is no reason we couldn't put up a null hypothesis saying that the random effect has 0 variance, right? And that's the same as eliminating a parameter, a variance, instead of a fixed effect. So anyway, a likelihood ratio test is one way to approach this model selection, where we now compare models of different complexity to each other in order to see if we can, which one we should choose, in a sense. Submodels or nested models, which is a term often used, and note NB, this has nothing to do with nested data that we will talk about in short time. So please don't confuse this term. Nested models has nothing to do with nested data. Okay, so I will not use this word. I use submodels, but you will see this in the literature if you start reading. So I prefer submodels now, not to make the confusion with nesting that we will talk about in the next session here. From the previous R session, where we did this, where we saw this likelihood ratio test, we had this model here, right? For this is milk production as an effect of the random sire, right? And this is what we now call the full model in our example. It's not a very big model, it's super small actually, but in that R session, this was what we would call the full model. And then we had the simpler version, right? The simplified version, the submodel. And notice that this submodel is actually a submodel. It's not a completely different one. It sort of comes from this full model by eliminating one parameter from this one, namely the mu, right? If you eliminate the mu from this one, you end up with this one. And this is the definition of a submodel. The submodel must always be sort of a subset of the full model, where you have reduced some parameter, eliminated one or more parameters from this one to end up with this one. So it couldn't be, this one could not contain some additional effects that you don't have here. Then it's no longer a submodel. That's important. So full versus submodel corresponds to now testing this exact null hypothesis versus this alternative hypothesis. Can you see that? So if this one is true, this one is the correct one. If this one is true, then this one is the correct one. So actually comparing the full model to the submodel is actually sort of comparing if this one versus this one is explaining our data. Then we fit models with maximum likelihood method. Both models are fitted with the maximum likelihood method to the same dataset. And that's of course really important that it's the same dataset. And what does it mean? It means find values for all parameters such that the likelihood function L is maximized. Right? We talked a little bit about this also in the very first week, actually. I mentioned it last week as well, because of the AIC criterion. It's also depending on having a maximum likelihood result, right? And here, again, we depend on that. So fitting a model with maximum likelihood means we have a likelihood function and we search for parameter values such that this function has its maximum. Think of it as sort of finding the top of the mountain, right? So this L function describes the shape of the mountain, and the different locations are the different parameter settings, right? The different combination of parameters values gives you a different location. And then you want to find the exact combination of parameters that puts you at the top of the mountain. Then, if you use the full model, you find the highest point you can find on the mountain with the full model. That's the maximum value for the likelihood function for the full model, this one. Then you do exactly the same with the submodel. Again, you find the maximum likelihood, but notice that the submodel gives you sort of a smaller terrain to search in. Here in this full model, you have more parameters that you can tune compared to this one. And then you will always find that the likelihood you find for the full model is always bigger or equal to the likelihood value you find for the submodel. And this has to do with the size of the parameter space you are searching in, right? Because this contains the same parameters as this one plus some more. So you have sort of more terrain to search over here to find the highest point compared to what you have here. And this one is always a subset of this terrain here. So this is exactly why you always have this condition here. The likelihood value for the bigger model is always at least as big as the likelihood value for the smaller model. Because with the full model, we search wider, sort of think of it as a bigger terrain. You want to search for the highest point in the terrain. And then you find the highest point for the full model is always at least as high as for the restricted model, right? But notice that this actually requires that the smaller model is a submodel of the larger. So this one covers a subset of the same terrain that this one. There is no terrain here that is not also covered here. And if the null hypothesis is actually true, then we expect these two to be approximately the same size, right? Because then the maximum likelihood you find by the submodel should be as good as the one you find with the full model, because having the extra parameter doesn't give you any extra likelihood, right? Because it should actually be zero, right? That's what the null hypothesis says. And then the likelihood ratio, which is this one. And here is a log likelihood ratio, right? So it's log of the likelihood. And instead of taking the log of the ratio, you can use the rule for logarithms and split it into difference like this instead. And there's this -2 in front of it. And why? Well, it's there because if you multiply this with -2, then it can be shown mathematically that this is approximately chi-square distributed with k degrees of freedom, where k is the difference in the number of parameters between the full and the submodel. So if this is the full model and this one is sort of one parameter less, then we expect this quantity here to be chi-square distributed with 1 degree of freedom. If this is 2 parameters less, then this is chi-squared with 2 degrees of freedom, right? If this is 3 parameters less, this is chi-squared with 3 degrees of freedom. And what does it mean? Here I plotted some of these chi-square densities for increasing number of degrees of freedom. So you can see for 1 degree of freedom, it looks like this. And it has an expected value here, right? So this likelihood ratio should be around 1. If it's much bigger than 1, it indicates that the null hypothesis is no longer true. This cannot be, because this holds only when the null hypothesis is true, right? So this log likelihood ratio should be around here somewhere, if it's 1 degree of freedom. If it's 2 degrees of freedom, the green one here, then the expected value is here at 2 instead. So these values can be slightly bigger, but if it's way out here, it's still possible to reject the null hypothesis, right? And for 3 degrees of freedom, the blue one here, this is the shape of the chi-square distribution. It has an expected value here at 3. And this likelihood ratio must be much bigger than 3 in order to reject the null hypothesis, right? But the p-values is then if your observed likelihood ratio is like here, then the p-value will be the area under the curve from that point and above, right? As we have seen before. So the larger the likelihood ratio, log likelihood ratio, the smaller the p-value gets, and the smaller p-value means we reject the null hypothesis. And if we cannot reject the null hypothesis, if we can reject the null hypothesis, we cannot simplify the model. It means then the full model gives us a significant improvement in likelihood value, right? So going from the smaller to the bigger model means we find a much bigger mountain. That indicates that the submodel was sort of too simple, right? And we should go for the... So if you have a small p-value here, it supports the bigger model. But if the p-value is large, you can stick to the smaller, and you cannot reject the null hypothesis except the smaller model as the choice. So, summarized, we may have several submodels, not only 2 like in my example. You have sort of the biggest one, which you can call the full model, and then you have a simplification of this one, and then you can of course have simplification of the simplification again. So you can actually do a full model selection here by gradually reducing and reducing and reducing parameters until this sort of stops, right? That's the same as a variable elimination, but instead it's a parameter elimination here now. A submodel always has fewer parameters, remember this. So we can eliminate both a fixed or a random effect. That goes for the same procedure. We test if the reduction reduces the model fitness substantially. And if it doesn't, we should stick to the bigger model then. I should also mention, since we last week talked about this AIC criterion, which is also based on these likelihood values, right? So we could actually use the AIC criterion again. So this likelihood ratio test and the AIC criterion are just 2 approaches to the same goal, you could say. So each maximum likelihood fitted model also gives us the AIC value, right? Here is the likelihood, right? Remember this formula from last week. And then you simply choose the model with the smallest AIC. That's also approach here. But if you want to sort of have a p-value behind, or you want to test specifically 2 models against each other and have a p-value as a sort of a support for your choice, then the likelihood ratio test will give that. the AIC has no p-values. You just simply look for the smallest one. Yeah, there is a difference, right? Because this involves a hypothesis test, this one doesn't. And you can have two AIC values almost the same size, and even one of them is usually tiny little smaller than the others, and you can select the smallest one. But in a likelihood ratio test, you have sort of you need to have sort of bigger differences in order to make the selection. So in a sense, the AIC criterion can be a little bit random, right, in what you end up as the chosen model, and then you can use the likelihood ratio approach instead. Okay, both AIC and likelihood ratios are general approaches who are not really has nothing to do with mixed models as such. They are used much wider than that, so please remember this. All maximum likelihood fitted models may use these approaches here. And the reason we mention it here now is because this is where it sort of pops up. But we could have used it in other contexts as well. It's a very general machinery, this. Let's move to the last sort of topic of today, crossed or nested data. And this is something we should say a few words about now, as we are dealing with the mixed models, because nested data is something that often sort of appears together with data sets requiring random effects. So what is the difference between crossed and nested data? Consider now data with two factors A and B. A has these 4 levels, B has 2 levels like this. Factors may be fixed or random. That doesn't matter really, even if nested factors are usually involving random variables. This applies to both fixed or random. Both fixed and random could be crossed or nested. Factors A and B we say are crossed if all the combinations of all levels have been sampled. Factorial design. Factor A is nested in factor B if levels of A is combined with only one level of B. And this is actually when I see this now, I see that this first one here is actually a little bit too strict, because the second one here is 100% correct. This is how we define nesting, and actually we should define crossed as anything except nesting. This is perhaps a little bit too strict, but in our examples and in our data set we will see this and this only. But you can have data who are crossed where you don't have a full factorial design. Yeah. But the point is that here we have all combinations of levels. Here we don't. The levels A is nested in B if A is combined with only one level of B. Some levels of A or all levels of A are combined with one level of B, and then some other are combined with another level of B, right? We can draw this as follows. This is how it looks like if it's crossed. You can put things, one factor along one dimension and the other factor along the other, and you have data for all combinations, right? This is full factorial. This is full factorial. All combinations are observed in our data set. All the levels of one factor, all the levels of another one, all the combinations are seen. Here is an example of a nested data set where we see that, and here A is nested in B, right? Because these two levels of A are only seen with one level of B, while these two levels of A are only seen with another level of B, So this is exactly what's in this second definition here. But you could actually have, as I have defined crossed up here, it requires this one to be full. You could actually have some cells missing up here as well, and still it's crossed, but then it's not a full factorial. But this is nested. And the difference between these two are what we will see in this course. Crossed or nested. We can also draw it like this, and this is a very common way of drawing it, and actually this is perhaps better than this table I showed you in the previous slide. So in this case we have a full factorial, right? Crossed. Every level of B is combined with all levels of A, right? But here we have the nested, and notice that many of these connections are missing over here. That's the big difference. So you can see that these two levels of A are only combined with one level of B, while these two is combined with another level of B. So why don't we always have data like this one to the left here? Because this looks like the better one, and it is. I mean, if you conduct some experiment, and if you can do it like this, it's the best. It's the most sort of informative data. But notice that this requires quite a lot of experimentation, right? Because you need to have measured the outcome of all combinations here. So in some cases, this is not possible, or it's for resource use or something like that. You cannot really combine everything with everything. You end up with something like this. Other cases, this way of combining things is not even possible. And then you are also forced to end up with something like this. So, I mean, nested data is not something we sort of choose, but it's something we sometimes have to choose. But keep this in mind. I mean, if you can do a full factorial experiment, it will always be the most informative one, right? But for some reasons, we sometimes need to stick to this here. We will see some examples where we understand why we could not really combine all here with all here. So nested data is also called hierarchical data, and that's most easily seen from this picture here, I think, because you can see there is sort of a hierarchy down here, right? You have the B's on top, and then you have the A's underneath. Here you could just as well reverse it, right? But here you see the hierarchical structure. It is more information in cross data. Yeah, that's what I exactly just now said. But it may be too expensive, or for some other reasons, all combinations in an experiment are not being done, and it may even be impossible sometimes. So in the cross data we have seen before. For instance, if you go back to week 3, we looked at this weights data, and that was a full factorial design where we had 3 diets and 4 supplements. So we had 2 factors with 3 and 4 levels, and we had all 3 times 4 equal 12 combinations in our data set. Very good data set. Nested data, last week we saw this fertilizer data, and here we actually have repeated measurements on each plant is then nested within plant, right? So you can think of, here is plant number 1 and here's plant number 2, and then you had the repeated measurements over time for plant 1, and then you had some other repeated measurements of plant 2 over time, and of course these measurements must be sort of nested within plant because you cannot make a measurement of plant 2 from plant 1. That's impossible, right? So it follows from the nature of the whole setup that it has to be nested in some way. All the repeated measurements you make of the same sort of random plant or random location or random unit they are always nested within that unit. And that actually applies to all replicates. If you do replicates, right? If you repeat the measurement of something, all replicates are always nested in something. Otherwise, they are not replicates, actually. So nested data are sort of more common than you should think, but we will see that we sort of ignore the nestedness of it if it's only at the replicate level. There is a potential for confusing this. Consider this data table here, where we have some response, okay, and we have two factors, A and B. Notice the levels here. This one has 2 levels. This one has also 2 levels. And by looking at this data set here now, it looks like this is a crossed data set, right? Since we have A1, B1, A1, B2, then A2, B1, A2, B2. We have all the 4 combinations in our data set, right? But this may also be nested. And the reason is that we sometimes get data which is not they are not very nicely explained in the table. So this is the crossed variant of this data set here. And the model that we fit to the data should look something like this. Here I have random effects, right? A and B, but they could also be fixed. It could also look like this. And notice that B1, B2 is now nested in A1. And here comes B1, B2 again, nested in A2. The point is that these two, B1 and B2, are not the same B1s and B2s that are over here. But it looks like they are, right? It looks like there are only 2 levels, but there are actually 4 of B. And this is not always displayed in the data table. So actually we should write it like this. This is the proper way of writing it. This is B1 nested in A1. This is B2 nested in A1. This is B1 again nested in A2. And B2 nested in A2. And now you can see from the indexing here that this is not the same as this, right? Because this is B11, this is B12. There are actually 4 levels here, 4 different levels of B. But it doesn't look like it when you look at the data table here. And this is sometimes, I mean, if you only have the data table like this, you would naturally think of this as a cross design, right? There are only 2 levels of B and 2 levels of A. But there are actually not. There are 4 levels of B and 2 of A, because the data is nested. And this then requires this notation of our model, right? So notice how the notation is. We say that this is level J nested in level I, right? So over here we sort of have no nesting, and then it means that you combine I and J like this, right? But here we have specified that it's not enough to say that J is 1 or 2. You also have to indicate the value of I to get the 4 levels, right? So this way of notation is quite common for describing nesting. The parentheses here and then the index that you are nesting in. So this is the precise notation, actually. Remember from last week, the fertilizer data. We had this growth of roots over time, which was weak in that data set. And we had 2 treatments, either a control or some fertilizer. And then 6 plants were measured repeatedly for each treatment level. And we should actually think of it like this, right? First we have treatment as fixed effects, control or fertilizer, 2 levels. And then we have plants. So under control regime we had 6 plants. And under the fertilizer regime we had 6 other plants. Right? So in that data set, the plants had these labels here. ID 1, 2, 3, 4, 5, 6 over here, and then 7, 8, 9, 10, 11, 12 here, over here. And that was a good labeling, you could say, because that so clearly demonstrates for us that we now have 12 plants. The factor plant has 12 levels, right? But in many data sets, you will see that these 6 plants here have the same label as these plants over here. Notice this difference, right? This was the original one. This is the sort of, I would say, the stupid way of doing it, but this is quite often done. And then, of course, if you don't tell the data analysis person that this is nested, it looks like the same plant here has been grown under control, and then the same plant has been grown again under fertilizer. But it's not, right? These two are not the same plants. ID1 over here and ID1 over here are 2 different plants. So in order to get that very, very clear, you either do as we did originally here, or you do the notation carefully. This is how we did the notation last week, where we were a little bit sloppy. We had 2 treatments, 12 plants, and 5 repeated measurements on each plant, while we should actually have written it like this to be 100% correct. We have, the fixed effect is here, right, of treatment of the fertilizer versus control on the intercept, and then we had a random effect of plant here. And notice now that now J goes only from 1 to 6. J goes now only from 1 to 6, right? It's plant number 1, 2, 3, 4, 5, 6 nested in 1 or 2, depending on if you are under control or fertilizer. And the same over here, where we had this random slope. This is the random slope, right? This is the random intercept. Again, we use the same notation. J goes from 1 to 6, but it's nested in I. And I is either 1 or 2. So this is plant number 1, 1, or plant number 1, 2. Or plant number 2, 1, 2, 2. 3, 1, 3, 2. Right? Nesting. And then we also have to use the same indexing here and here. And notice here at the residual, the replicates, right? The 5 measurements over time made on each plant is also, so these 5 measurements over time is now nested within plant. J counts the plants, right? Which in turn is nested in treatment here. So we have sort of a double nesting, right? Here. And this is, I would say, the 100% correct notation for this model. If we were really picky about it, we should have written it like this, where J goes only from 1 to 6. Because if you notice up here, and I think I mentioned this in an exercise last week, or perhaps it's this week, notice that J goes from 1 to 12 up here. And if you look at I, J, K here, and you look into the data set, you will see that you don't have all combinations of I, J, and K. For instance, if I equals 1, you are in the control group. there is no plant number 1 in the control group in the way we numbered the plants originally here, because plant number 1 is in the fertilizer treatment, right? Plant number 2 is in fertilizer. Plant 1 up to 6 is in combination with I equals 2, while the plant 7 to 12 is in combination with the I equals 1 here. So actually this way of writing the model is not 100% correct in terms of the indexes, right? Because all of these combinations are not really in the data set. But it's usually good enough. And I mean, this way of writing the residual error term is always used. I've never seen this way of writing it, even if this is the correct way of doing it. So people are sloppy even in textbooks and about this, I have to say. A little bit sad though, because it's always nice to be, at least when you're going to learn something new, it's always a good idea to be very precise, right? Because there are plenty of things to be confused about if you're not also confused about the notation. So I prefer to try to be extremely picky about the notation so that everything is 100% crystal clear at that level at least, right? And then we can sort of worry about the real confusion. So that's why I also use the Greek letters, right? And the Latin letters. And this notation here, I should also actually, I must confess I may be a little bit sloppy myself. Mixed models and nesting. So in mixed models, we often, or in data set that require mixed models, you could say, are also often data set with some nesting. Mixed models or the random effect models means nested data in the sense that repeated measurements within a unit is always nested within that unit. Random unit can also be nested within a fixed effect. We will see that in an exercise this week. And we can also have a random unit within another random unit, actually. That's also not too uncommon. And there is a horrible, actually, but big example in the R book about split plot design. You can always have a look at it if you like, but I find it too complex to be a good example for teaching. But there you can see random effects nested within random effects. But I would say do it if you like. It's not really an important example for this course, but since I mention it here. Yeah, we fit the mixed models for nested data slightly different from if we have cross data. And we should have a look at that in R so that we know how to treat this differently. And that is sort of important for applied statistics course like this. Make certain you know what is crossed and nested. Yeah, this is super important. And as we have seen, the notation and the way we sort of display the data in the data table can be important here. Fitting crossed data as nested or vice versa may give very different conclusions. And I think that it's the vice versa that is sort of the typical error we make. That data are actually nested, but we think they are crossed and then make the error that way. So we fit nested data as if they were crossed. That would be often or usually a very severe mistake to make, because I mean, yeah, we will see some examples of that in the exercises. Remember that crossed data is sort of more informative. We believe that our data are more informative than they actually are, right? That's what we end up doing then. So let's go and have a look at this in an R session again, and that sort of completes our session today. Let's have a look at the last R session here about this sire herd data. So what is this actually? Let's have a look at this data. And like that. Sire herd. Again, we have these three sires, sire 1, 2, and 3, and their daughters producing milk. So that's the same response as before. In addition to the sires now, the fathers of the cows are also now living in different herds. You can think of them as different farms, different environments, right? So now we can see that each of the three sires here is father of 2 cows each, and each of these 2 cows, or each of these 6 cows, all these 6 cows live in the same herd, producing milk, right? And then the same 3 fathers are also fathers of some other cows, 6 more cows living in another herd here, also producing milk. And all in all, there are 4 herds, right? And it's the same 3 sires that are the fathers all the time, so these are actually crossed data, right? These are cross data because each sire is combined with every herd, and every herd with every sire. So there are altogether 12 combinations, and since there are 2 cows from each combination, there are 24 data points here. We can also imagine now that when we are looking for breeding of sires, right? Breeding. Which sire, or should we actually look for the best father in order to get the best milk production? We should now consider the variance in fathers or sires here related to the variance in herds, right? Because we could easily imagine that it's the herd that is important for the milk production, right? So the variation between herd is big and sires is not so big, and then it's no point in going hunting for the best sire because it depends on the herd anyway, right? So we want to now have a model where we look at the response milk production as an effect of both sire and herd, and both of these are natural to consider as random effects, right? Because the 3 sires we now have is only a random sample of all the sires we could have had, and the same for the herds. These are only 4 out of many herds we could have considered. Okay, so the data set is crossed, right? Because we saw every combination of herd is seen together with every combination of sire. So the random effect model would look something like this. Straightforward, right? This is the effect of sire then, and this is the effect of herd. And so we have 3 sires, right? I is 1, 2, or 3. And B is the effect of herd, which is 1, 2, 3, or 4 in this data set. Before we fit the model here, let's look at the nested subset of this data. So let me copy this code here and make a subset of this data. So now I take the sire herd data table and I just filter out some of the rows. And notice now I want to have the rows where sire equals 1 and herd is either 1 or 2. Or sire equals 2 and herd is either 3 or 4. So this gives me nested data. And then I just mutate so that we lose all this factor information, because actually when you inherit, notice now I only have sire 1 and 2. The sire number 3 is left out now. But sire will still be a factor with 3 levels unless I sort of eliminate the whole factor property, you could say. So let me run this line here and let's have a look at this sire herd nested. Much smaller table. And notice now we have only 2 sires, 1 and 2, but we have 4 herds. And this is nested, right? this is nested because these two levels of herd, 1 and 2, is only seen in combination with one level of sire. And these two levels of herd, 3 and 4, is also only seen in combination with one level of sire. So these data are nested. And that's really apparent here now. Now, what we often see, and we saw this earlier, is this, namely that these factor levels of herd is actually displayed as 1, 2, and then 1, 2 again, making this look like a cross data set. And that's what I try to do here. I just now replace every occurrence of 3 with 1 and every occurrence of 4 with 2. So and then I make this into factors again, right? So let me run this line of code just to, this is how tables like this sometimes look like, right? And notice now that if we just see this table here now, it looks like if the data are crossed. Now we lost this nesting information here. So that must be given to us sort of outside the data table, that herd is now nested in sire. And since we have this information now, what I would actually do right away when I have a data table that looks like this, and I know that herd is nested in sire, what I would do then is immediately this thing here. I will then create a third column. Let me copy it into the code here. I would immediately create a third column here that tells me this nesting information. And notice I call this column herd.sire, because this is now the information about that herd is nested in sire. And here I use this colon, this is the interaction operator in R. And these are factors, right? This is a factor with some levels, and this is a factor with some levels. So now we get the interaction between the levels. And the reason I call it this name is I like to use this dot notation because that's inherited from the internet notation, right? When you visit a location at the internet, you see this dot notation, an internet address, right? And it always starts with the, sort of the most local information first, and then it's nested in, nested in the more sort of the level above, which is again nested in the level above, which is again nested in the level above. So for instance, nmbu.no indicates that this is NMBU nested in Norway, right? Because there could be an NMBU also in Denmark, then it would be nmbu.dk. So that's why I think that if we invented this notation for describing nesting today, this is how we would have done it. But instead of this parenthesis and stuff that we have here. So here we have the notation that is used now with this parenthesis, J parenthesis I, right? So now we have the effect of sire here, and then effect of herd, which is herd number 1 or 2 nested in sire number 1 or 2. But I'm sure that had we invented this notation today, we would have used j.i instead of j parenthesis I because of the internet. That's my guess though. Okay, so let's have a look at this. No, I must run this code first, of course, like that, and then we can inspect our table. Yes. Actually, I would now, if this were my data table, I would replace this column here by this column here. Because this column here is only confusing. This is the herd information. This is the herd information. It's herd nested in sire, and here we can clearly see there are 4 herds in this data set. There are 4 different levels of this factor. This is not clear in this column here. So think about that. Keep things simple. Let's do the model fitting. First of all, using LME as before. How do we fit data if they are nested? That's what we are looking. So now we look at this nested subset, and we want to fit the model in this case. So we use the LME with the milk as response. That's no difference, 1 intercept. And here's the random effect. And notice the this notation here. This is how you describe this in this LME function, nesting. And how should you read this term? You should read it like this. We have a random effect affecting the intercept. And the first random, there is actually 2 random effects here. The first one is the random effect of sire. That's what this partly says. Plus 1 more random effect also on the intercept of herd nested in sire. So actually this notation here tells R there are 2 random effects. First of the first one, then of the second one nested in the first one. Let's run this and see what comes as output. Here is the output, and then you can see the first random effect is this one, the random effect of sire, having this standard deviation here. This is the sigma A. And then the second random effect is herd nested in sire. And this is the output here. This is a strange way of outputting it, I would say. I would have written it sire/herd as we did here. I don't know why they decided to make it look different here, but it means the same thing. And here we have its standard deviation of herd, very little, almost 0. And then you have finally the residual standard deviation, sigma E. So this is sigma B, and this is sigma E in this model, in terms of this up here, right? Sigma A behind this one, sigma B behind this one, sigma E behind this one. And the fixed effect is displayed as before. So notice this way of notation, the slash. It doesn't mean divide by here. It has a different interpretation. It means nesting. And it's this one which is nested in this one, right? It's sort of nesting. It displays it in the wrong way, I would say, compared to what I did up here. I would have herd before sire when herd is nested in sire. Okay, let's see how this other Elmer function does it in R. This is an alternative that we saw previously for fitting mixed models from the LME4 package. And it's slightly different, but also very similar in a sense. So we fit Elmer model, the same response, the same intercept. And remember, the difference is that you don't specify random equals. You just add the random effects to the formula as you would any fixed effect also. But you indicate it's a random effect in this way. First a parenthesis, then the name of the fixed effect that you want to sort of modify, you could say, or by this random effect, and that's the intercept. And then you have the same notation for describing this nesting. So again, it's interpreted as first a random effect of only sire plus a random effect of herd nested in sire. So that's the same. And if we fit this one, You get a small warning here, and the reason for that is that now this standard deviation was actually estimated to 0. So previously here it was not 0, it was almost 0, but not entirely. Now it was actually 0, and that's why we get this message, because remember, variances cannot be negative in REML estimates. So we are at the boundary now. Yeah. And the differences between the two outputs here are due to some small numerical differences. So they are more or less the same, right? Close to 0. Here is another way of fitting the last model, and this is important. Let me show you this. This is important, I think. As an alternative to using this notation here with the slash, I fit this Elmer model in this way instead. Notice I now specify first only the random effect of sire plus the random effect of this variable that I created myself, herd.sire. Because this one now is just another random variable, right? If you go to the data table. So I don't use this column at all. I only use this one and my newly created one. And I think that actually this is in many ways a better way of doing it. First of all, because by creating this column here, you clearly have sort of made it absolutely clear that this is a nesting of herd inside sire, right? The nesting information is in this column. And also in the model here, it becomes clear that actually this fits two random effects. First one of sire and the second one of herd, which is nested in sire. I think this is actually better, at least for pedagogical purposes, better than this notation. And it gives exactly the same result. If you don't believe me, you can do it yourself. Actually, in the exercises, you will also need to do things like this. And why is that? Because sometimes we want to fit a random model here, which is nested inside a fixed effect here. What if sire was a fixed effect in the model? Then this way of coding it will not work, because then it will be also fitted as a random effect, right? But here, down here, it's not a problem, because we could easily make this column here by nesting a random variable inside a fixed one, and then just leave out this one here, include it as a fixed effect instead, and still use this one as a random effect, without having sire as a random effect, if we want to. You will do that in an exercise, actually. So notice this way of fitting a mixed model in using Elmer. Could be a good idea. Model selection again. Let's just have a look at this likelihood ratio test. We saw now that this effect of the herd was very small and even 0 here, right? The variance is 0. Could we now just eliminate it from our model? That's not so a nutshell to think, right? Could we just leave this effect out? It has almost no variance, right? Or at least it looks like it from the estimates. So we can put up the null hypothesis saying that sigma b is actually 0 versus sigma b is bigger than 0. And this is one-sided, right? Because it cannot be negative. How do we test this? Well, we do the likelihood ratio test again. So then we fit an alternative model under the null hypothesis. And that's simply using the same as up here, but leaving out this term, right? Leaving out this term. So let's do that. We fit the model without the random effect of herd. And then we can compare now this simple model to the more complicated one where herd is included. And what happens if we do it? Well, we see that the p-value is 1. There is no significant effect of, or there is no significant increase in fit by going from the simpler to the more complex model. So we should stick to the simple model. The null hypothesis cannot be rejected. We consider the null hypothesis as being true, sort of. And sigma b is 0. We can ignore this herd effect. That's the conclusion. We can also see it from the AIC values. The simpler model comes out with smaller AIC than the more complex one. Null hypothesis model is the best. So in this case, we can actually discard this term. There was so small effect of herd that this is not important at all for this milk production. Let's finally have a look at how things can go wrong if we confuse crossed and nested data. Let's first look at the full data set where we had a crossed data set. We have the full data set, right? Crossed data. We fit a model as if the data are crossed. So this is sort of the correct way of doing it. And here is the output. We estimate this, the standard deviations for herd and for sire. So for this full data set, herd really had some variance, but much smaller than sire. If we go back and do it wrong, if we actually think that herd is nested in sire, but it's not, what happens then? You can see that fitting the model is not a problem. What is the result? It changes a little bit, but not super much. If you look at the standard deviation for sire, 325 to 317, not super much difference. A little bit smaller. The herd standard deviation shrinks more, but it's not dramatically different. So it's an effect, but it's not dramatical. Let's do the other way around, where we have actually nested data. And first we fit the nested data with the nesting, right? As we should do. And we did this before, so we know the output. We will get this 0 standard deviation for the herd and quite a big standard deviation for sire. What happens now if we think that sire and herd are too crossed, right? Because we have this herd column still, right? So we could make this error if we didn't have this column over here. If we only had these two columns here, we could easily think that these are crossed, right? And then fit the model like this with sire and herd as separate crossed variables. And look at the effect of herd now. This is very big compared to 0. Right? So now it looks like herd really is an important variable here. While when the nesting of the data was taken into consideration, it was 0. So this had a huge impact. So please make sure you don't do mistakes like this, because it could potentially influence your results severely. And I think that my best sort of advice is to, whenever you have nested data and you have this silly notation here, I have to say, please replace it with a column like this one so that you don't confuse nested data with crossed. If you have this one, you will never make the confusion, right?